We are going to simulate in FEKO a microstrip line. First thing, we have to somehow find the dimensions for the 50 ohm line impedance. For instance, we have this application here online. We are going to try FR4, which is the most common substrate used for RF and microwave. It has, here we can type in the dielectric constant, 4.3. Let's take the height of the substrate to be 1 millimeter and frequency 1 gigahertz. It's a TEM type structure, so it doesn't matter for our purpose. And the impedance that we are going to use is 50, and just type in any length, 10 degrees for instance, it doesn't matter the length. We're interested only in this width here, dw. We type in synthesize and you have this 0.94 millimeters. This is the width of the strip to get 50 ohms here, measured here. Well, once we have these dimensions, the dielectric constant, the height, and the W, the width, we can go to FEKO, CAD FEKO, and create a new model. Then we just inform FEKO the variables. For instance, first variable is F max, maximum frequency. For this case, 1.5 gigahertz. The minimum frequency of our microstrip line is 800 megahertz. Our substrate is going to have 20 millimeters in one direction and 60 millimeters or 6 centimeters in the other direction. The thickness of our substrate is 1 millimeter. The width of our line to get 50 ohm is going to be called W50. 1.94 millimeter. And this last parameter is the offset 3 millimeters. I just forgot, epsilon r is 4.3. Now we are going to construct the structure as we move to construct cuboid, and then we start with our substrate. We picked the base center option. We are going to leave the plane at z equals to 0. So this is supposed to be minus h sub, minus 1 millimeter, as previously defined. Width is our y sub, and d is x sub. Here we see our substrate. Next, we create our media. Right-click dielectric medium. For the sake of make it simple, just type in epsilon r, 4.3. It's frequency independent. It's the simplest case possible. Create. And then you can see that our cuboid here, cuboid, we right click on regions and you just switch it for dielectric 1, which is our FR4. And you can pay attention that it's lossless. We left with 0 loss tangent, so it doesn't have any kind of loss. This is our cuboid. Next, we are going to construct the microstrip line. And the microstrip line, we move to rectangle. The same option here, base center option here. And here we get the Y sub plus offset, which is 3 millimeters. And D is W50. Create. You can see here that the microstrip line is longer than the substrate, which seems to be off, seems to be odd a little bit. The problem here is we need to do this way because we are working with a finite substrate. FEKO, you have the option to operate with an infinite substrate, but in this case we are going to make it a finite, so it's more, it's better. The simulation is more complex, but it pays off because we have better results if we are going to compare with measurements and posterior analysis. You can see here that this rectangle has to be fed somewhere. So we need to place parts here. The part we're going to use is called, you can see here, this edge part. This edge part has something that it requires to be completely embedded on the same substrate. So either we place the part here inside the dielectric, or we can move it outside the substrate. In this case, what you need to do, you need to make a connection, a metallic connection with the ground plane. How we do this? We are going to ask for, well, you can, another thing, you can write down the dimensions, etc. It's doable, you can do it that way, but it's easier using the pick tools of FEKO. And by pick tools, you just type at the same time Shift and Control. And as you can see here, I have available, I'm moving my mouse here. All these pick points, they are available without the need to compute them manually. So how are we going to use this? Well, we move to Construct, Rectangle, and here we need to make a vertical rectangle here. So the work plane should be shifted, you see, like that. It makes sense. We have to keep in mind that this 2D objects, the surfaces, as FEKO call them, they are all the time placed here on this plane. So it's consistent with what you are going to construct here. So then we move to geometry, and the active area is this stressed in yellow. We type in Ctrl Shift, and now using this option here, we pick the middle point, as you see here. Twice, it's done. Now our plane is aligned here. You can see that this shadowed square is showing where the rectangle is going to be constructed. That's exactly what we need. We just need to type in the W and the D variables. We can type in W50 and H sub. You see, we have to move here. As you can see here, it's upside down. This variable is here, and this is here. Now it makes sense. The two variables, they make sense because they are exactly this width of this rectangle is the same as the former one. And don't worry about getting it being too high. We just type in create and it's done. Now we need to move it. Move this rectangle. Again, we can make some computation by hand, but it's easier to type in rectangle here, transform, translate. Again, from to, it's in yellow from, Ctrl Shift, you type in here. Now it's yellow to. Double click, okay, it's moved. Same thing for the other side. Construct, rectangle. This thing here is not correctly aligned. We move to work plane. It's not this, it's not that. This is the right one. Now we move to geometry. This is the yellow one. Ctrl Shift pressed. Middle point here. Give it a zoom. Now H sub W50. We have to choose this one here. It's not the correct one, it's the upside down again, W50, H sub. Now it makes sense. Great. Done. We need to move it. Select the rectangle is already selected. Transform, translate, Ctrl Shift here, Ctrl Shift here. All the numerical values are updated on the window. FEKO does that for you. Okay, it's done. Really easy. Much easier than making complicated computations by hand. Next, we need to make a short circuit with this thing here, with this ground plane. Construct, rectangle, work plane. Where is the work plane here? It's correct. You see here, it's correct. It's correctly aligned. We just need to bring the work plane to this point. Geometry, Ctrl Shift. We pick the middle point here, as you see, give it a zoom. And now W50. And here offset over 2. Offset over 2 is exactly this distance. As you can see here, it's wrong. We have picked the wrong order. It's much easier just watch and see if it's working or not. Create. Again, select this rectangle. Select here. Transform, translate, Ctrl Shift, from here to here. Okay, done. The same thing on the other side, using the mouse to rotate the structure. Again, we are going to go here, construct rectangle. It's correctly aligned. Don't need to worry. Move it here. Base center, middle point here. Done. W50. Offset over 2. Let's see if it's alright. Yeah. No, it's the other way. W50. Done. You see here. Create. We just need to move it. Select, translate, from, to, Ctrl Shift, done. It's perfect. Now, what's missing? The part. The part, we need to divide this vertical strip, metal strip. This and this here, those two metal strips. So it's easier if you just call them, give it another name. We go to rename. Let's call it part 1. Right click, part 1. See if it's correct. Yeah, it's done. It's correct. And this here is double click, rectangle 2. Double right click, rename, part 2. There we go. Part 1, part 2. You see the yellow is the color that the object takes when it's selected. Now, pay attention because this is very important. We are going to select part 1 and just go to construct, split. Split is asking, it's like a blade that cuts the chosen object in two. The blade is the grid. So as you can see here, if you imagine the blade, it's not going to cut this structure in the middle. So we need to move it. So again, how do we move it? The origin of this blade, it's Ctrl Shift. I'm moving here with the mouse. When I reach the middle point, click here, create. It's done. I have 1/2 and 1/2 here. We make the same for the other side. Here, select the other part, split. We have to move it because a blade or a knife here is not going to cut anything. Ctrl Shift. You see here is stressed this middle point, double click, updated values here on the FEKO window, create, done. Now we can take this. You see there are other objects. FEKO gives the name split front and split back. Split front and split back, we just select this front 2 and back 2 and you make it a union. The same for back 1 and front 1. Shift, selecting both, union. Now we have these structures here, union. What's the meaning of the union? Union says that all these structures are electrically connected. Otherwise, FEKO cannot know if they are connected or not. So now the union says these structures are not floating in space, they are actually connected. We can very easily define the part. Union here, you select it here, and you just move it. The part is in source load. The part we're going to use is this edge part. It's just easier if we select union to the two faces. You see here in yellow, and shows up in edge part. Just select edge part, and now we have the both faces here. You need to be very careful because we have to find which is the part that connects to the ground plane. It's this one here because it's yellow, and this is the negative part. You are just moving to the negative face. Automatically FEKO creates this edge part here. We move to the other side. Here we select this union. regarding part number 2 that we just created. Select these 2 faces with Shift, and we do the same thing. Type in edge part. What's the rectangle that goes under? This is the one. Because it's yellow, just move to negative faces. It's done. It's created this edge part. Basically, that's everything we need to do. Now we have to just pay attention to the materials. Before that, we just select everything, all the objects here. And again, because they are all the objects, they are in contact with one another, we just move to Construct Union. Now FEKO knows, from the viewpoint of a user, it doesn't make any difference, but from the viewpoint of the software of FEKO, now he knows that all of the structures are connected. The last thing we need to do regarding the object itself is just checking the materials. Let's go then. Well, first thing, this face here is the strip. Right click, properties, is perfect electric conductor. This face 11 is this strip here. It should be perfect electric conductor. This face here is the ground plane. This face here is supposed to be a dielectric. That's fine. These 2. Fine. All these are correct. This here is also the default. This here is also probably default. So you just need to check the strips. PC. This one here is PC. PC. What else? This here, the part is PC. PC and PEC. And here, PC, right click, PC, right click, PC, it's done. This thing here, PEC. Everything seems to be all right. This here, PEC. I guess all of them are fine. It was easier moving these strips to PEC when we created them, but regardless, I guess it's okay. In case we have some weird result, that's going to be the reason we had bad results. Probably one of these strips was left as a dielectric. Then it's done. We can assign the frequency and source load. We are going to use continuous interpolated range, linear spaced discrete points, because it's faster. F min, F max. How many frequencies? Let us put it 11. Okay. And now what's important? There are 2 ways to simulate this structure with FEKO. The first one is asking the S parameters. S parameters are handled, and we have the correct S parameters, S21, S11, as expected. The other thing is, if you want to see the fields, that's our case, we cannot use the S parameters. So what we do, we define the ports, in our case is this edge port, and we assign one of the ports as a voltage source. So you can imagine these ports here as being connectors. On one of these connectors, we are going to attach a signal generator, a power generator, which is this thing here, as you can see, P1. It's 50 ohm impedance. We just add it. And what about the other one? If we leave the other one here, it's going to be a short. So in real world, if you're going to see a perfect through a transmission line with no reflection, theoretically no reflection, we need to attach here what? A load. So we go to add load, and now we pick port 2. This is going to be a pure 50 ohm complex impedance load. So that's it. In one side you have the voltage source here, and on the other side we have the load, the 50 ohm load. That way it means we have this connector in this side with a cable to a signal generator or power source, whatever, swept covering the frequency range, and here we have a simple coaxial 50 ohm load. That said, we are going to ask for what? The requests. Let's ask for near fields. In near fields, we can get pretty neat pictures defining planes. So the first plane we are going to select, as you can see here, is the plane parallel to this structure, parallel to this thing, but a little bit higher. So the plane here is correct, as you can see here. I don't know if the movie you are going to see here, it's correctly aligned. We don't need to switch to rotate the plane. We are just going to give it, for instance, 1 millimeter height, H sub, H sub. And now we can get the starting point. We can type in any numbers that you need, but just Ctrl Shift. We select this point, and the second point, you see this is yellow here. I kept held Ctrl Shift. I click here. This is the first plane. Number of field points. This thing here is Ctrl C, Ctrl V. I just correct here the N. As you can see here, you see exactly as expected. As you can see here, you just need to define the number of points along the U and V, because that's where we have a variation. 21, 21. Great. This is the plane where the near field is going to be swept over. We are going to also get a plane like a blade orthogonal to this dielectric. We go to the same near fields. Now the plane should be, you see, swept like this, wrong. This is the way, exactly in the middle as expected. I just move it here. And now we can get, for instance, U. As you see here, it doesn't change along the X or U, but here we can get, for instance, minus Y sub, Ctrl C, Ctrl V, Ctrl C, Ctrl V. Here, this is a random thing. Just need to switch like that. There we go. It's a little bit too big. divide by 2. Divide by 2, just to make it smaller. Not bad. Again, V and N are the variables where we should get our field sampled. Great. Now we have the two near fields. One is here and one is here. Mesh, create mesh. Pretty simple, it's done. Solve run, CEM validate. Nothing seems to pop out telling us we made a mistake. Okay, and we can FEKO solver. We need to save it with any name. Microstrip 1. Save. It's running. So when you see here 100% both, you can move to the post FEKO and you see the structure. First, let's see our Cartesian, type in Cartesian and just drag and drop voltage source. There you see reflection coefficient, which is supposed to be the same as our S11, the scattering parameter. Just one part, you just have S11. We move to dB. You see a pretty nice matched line here, minus 15 dBs. We are just getting a small range, but you see it's actually 50 ohm. You can check the Smith chart. Just type in Smith chart, drag voltage source here, and you see it's FEKO tells us that there is a slight inductive behavior for this frequency. All right, and we can move to the near field. The near field, we just go back to the microstrip 11 and click near field 1, right click. Here you have 3D view. There we go. This is the electric field here for the frequency of 800 megahertz. As you can see here, as expected, it goes all the way from one side to the other. This is the electric field. This is the magnetic field, as expected. And you see that we have the effect of the finite ground plane. If you make a posterior analysis, we are going to see that the results are worse than those that we would have comparing to this infinite ground plane, infinite dielectric. This is much more loyal to the real world. Add new 3D view, and this is what? The another cut. And this is nice to see, again, the effect of the finite ground plane. You see here, we have, let's move to the highest frequency, 1500. You see here what happens. The field is concentrated on the edges. And this only happens because we have a finite substrate. And here you can see the electric field and also magnetic field in magnitude. As expected, the energy is being carried out by the strip, right? So that's everything I wanted to show. Thank you very much.